So on page 5, these are not really calculation type problems. It's still early on in the packet. It's still just force concepts. And so that's what this page is about. There are some nuances with each problem, so we'll work through them together. And my goal today is to get through at least page 8 started. Okay, there's 2 big problems there. I at least want to get the top problem done. And so this page has basically 5 PowerPoint slide drawings. And so they're each an individual problem. So we'll take a look at that top left. We've got 2 objects. I'm going to call it A and B, or if that confuses with our questions, ABC, if you want to call them 1 and 2, red object, green object, however. Now there are some arrows, some vectors. They're supposed to represent forces. So they don't really say if it's gravitational force or a tension force, but it's some kind of force. So maybe F1, F2, and then F1, F2. This could be a top view of 2 kids pulling on a toy, right? And so just in the general spirit of forces and Newton's laws, what could be true, keyword could object A and or B be staying at rest? So is it A only, B only, or both? Which one could be staying at rest? A could. How do you know? Right. Don't you get a ruler, but yeah, the intent was F1 equals F2 on object A. And so it's balanced, right? Could an object remain at rest if there's balanced forces acting on it? Yeah. But then on object B, you don't have a balance, right? And you could go in and draw components for F1. There's an X component and a Y component. Maybe the Y component balances F2, but overall, nothing balances the X component. And so it can't stay at rest. If it started at rest and you did these 2 forces, it would not stay at rest. Question B, could these objects, A only, B only, or both, be moving? A only, B only, or both? Could be moving. B could be moving, right? We've already talked how it has an unbalanced force. What about though A, if it has balanced forces, could it be moving? Be more specific. Tell me how it's moving. Constant velocity, right? So remember, this Newton's first law, hopefully I said the word equilibrium last time, state of equilibrium, okay? It's for objects with balanced forces. It could be at rest, or you can be at a constant velocity. And so, yeah, I'm going to put A and B both could be moving. A could be moving at a constant speed, and B, well, we know it's not going to be a constant speed, but yes, it could be moving. Question C, who could be accelerating? Just B. Yep. Because we just said A could be moving, but it would have a constant velocity. You can't be accelerating if you have a constant velocity. Everyone good on the first example? Top left. Top right. This is going to be our first look at a system. And so I think so far we've only looked at the forces on a single object, but get ready. What if I stack a bunch of single objects on, I think of a stack of books, right? Or stack your presents maybe, okay? You can take a system approach. And so here, situation A, B, C, we've got different stacks of different books. Rank, firstly, the normal force on the top block. Y'all, prepositions are pretty important. It tells you who to draw a free body diagram or force diagram. For right now, it's the same thing. Later in the spring, we'll get more difference. But it tells you who to draw a diagram for, okay? Now, we do have to make an assumption. These books and all these stacks, we'll assume they're on a surface. Later on, it'll talk about a floor. But we'll assume they're just sitting there, okay? So everybody is at rest. And so with that, to draw the force diagram for just the top block, okay? Now, they all have a top block. And so no one's moving. They're all going to have the same kind of diagram, maybe different magnitudes, but they all have the mass. So a gravitational force. What other force is working on just the top block? It can't be just gravity or it's falling towards the earth. There's some kind of support force, right? By whatever the bottom block. Well, isn't the bottom block just another surface? Can't we just call it the normal force? What direction is the normal force on the top block? Straight up, right? Perpendicular to the surface. And so if they're all at rest, these two forces are going to be equal and opposite. Now, I kept the Drake meme up in the beginning. I said it's worth repeating. I repeat it a lot. Is this Newton's first law or second law or third law? This equal and opposite, gravitational force. Newton's first law, I see. Yes. And so if they balance, if the forces balance on a single object, it's Newton's first law. Okay, don't worry, you'll see an example of third law today, a couple times. And so they each have just a gravitational force and normal force, but who's going to have the greatest normal force? Well, who has the greatest gravitational force? Situation A, B, or C? What is gravitational force? Did they give me newtons? No, they gave me kilograms. How do I go from kilograms to gravitational force? Do y'all remember the equation for gravitational force, AKA weight? What's our equation for weight? We talked about field trip to the moon. Our weight changes, but what doesn't? Our mass. So it's mass times that acceleration due to gravity on the Earth, on the moon. We'll assume we're on the Earth today. And so gravity, 9.8, 10, either one. But notice who has more mass. A is equal to B greater than C. It's solely based on the mass of the top block, okay? All right, question 2. What about the normal force of the floor on the bottom block? Now, traditionally, I would say we'll draw the force diagram of the bottom block. We're not going to get nitty-gritty necessarily with systems right now, but think of it a different way. Take a system approach. Isn't the floor supporting the whole stack of books? A whole stack. The floor is supporting everything. And so if you look at it as a system, then if you want to kind of redraw at least A, don't look at it as 2 books that are 40 and 100. Look at it as one collective, as 140 kilograms. And so if you look at the stacks or the system, who's the floor going to push up the greatest? Well, a force diagram of the system would be the gravitational force of the system. And again, everybody's at rest. And so the floor is supporting the system. So who's going to have the greatest floor force? Well, who has the greatest system gravitational force? Y'all tell me. A is 140, B is 90, and C is 110, okay? It doesn't matter that it has 3 blocks. It's about the total mass of the system. And so we'd get A is greater than C, greater than B. Good deal? So final answers there are those. All right, slide 3, or middle left, however you want to say that. It's a simple, just draw a diagram. So what do we see in here? And so I'm going to use my microphone, which is a mass. There's a lanyard, there's a string. And so all you're looking at is a mass on a string, microphone on a string, and it's going back and forth. We call this a pendulum, but we're not doing pendulum physics right now. It's saying freeze when it's going northeast. Now, it's moving. They say there is a velocity vector. We're not looking at the max height where it might come to a split-second stop. But if it's moving northeast, draw a free body diagram on that block or object ball at this moment. Remember, these diagrams are snapshots in time. And so tomorrow, maybe it's at the peak, maybe it's at the lowest point, okay? Those are technically different diagrams. And so right here, right now, what forces are acting on this ball? Have you noticed the every time force? All our masses have mass. We always have a gravitational force. What else? Tension. The rule for tension, remember, it pulls parallel to the string. And so if the string is in the northwest direction, it's going to pull northwest. Now that arrow there, I don't know if you can tell, but it got a little squiggly. Something's up with my stylus. So that's supposed to be a straight arrow, not a ziggy-zaggy arrow, okay? And that's it. Oh, I'm not labeling it northwest, FT, tension. Now the question comes up because we did some balls in the air last time. Do we include air resistance? And so they didn't really specify yay or nay, but overall, y'all, air resistance really plays a role if it's a falling or free fall object. With a string attached, you really have insignificant or very little air resistance, at least playing a role, okay? Tension wins, okay? Now, if the string is cut, that's a different story. By the way, AP loves to cut strings. Part A, string is there. Part C or D, now the string is cut. It turns into a new problem, right? It becomes a projectile problem, 2-dimensional. So that's it. To the right. Now the picture can be a little misleading, hence why we need a little explanation. This is supposed to be a convertible car. So this right here, that line, is supposed to be a windshield. It's not a catapult system. The ... to our little pebble, rock, bug, whatever you want to call it, maybe this pebble is on its way to hitting the windshield. That's the intent of the picture. But some students without explanation, they're like, is the windshield launching the pebble? And I can understand that interpretation, but that wasn't the intent. So maybe you've been in a car, the bug hits the windshield, right? Or a pebble, worst case, pebble hits the windshield. Rank the force, now watch this, I'm going to add 2. The force on the car by the pebble, and then the force on the pebble by the car. So this is when the pebble hits the windshield. And so if we fast forward, you know, here's our car, There's our windshield. When the pebble hits the windshield, the forces that they're talking about, well, the windshield is going to have a force on the pebble by the car to the right. And at the same moment, isn't there a force on the car by the pebble to the left? Rank these two forces. What say you? What do you think? Which one's bigger? Say again. Everybody says, oh, the force on the pebble. The car hits the pebble more, right? Because if it was a bug, the bug dies, splatters, right? So we say, oh, the car hits the bug harder. But that's actually not true. Now, the bug does die, but it's not because of a greater force. Did you notice I got nitty gritty? Did you notice I drew two objects? It was the force on the pebble. It was the force on the car. Hint, hint, what would Drake say the answer is? They're equal. What? This is a Newton's third law example. I hit you, you hit me, right? The bug hits the windshield. It gets an equal and opposite force on the car. Y'all, here's why. The bug doesn't change the velocity of the car because the mass of the bug and the mass of the car are very, very different, yes? And so the bug dies because there's a greater acceleration on the bug. It can't handle it, right? Okay. Does this make sense? Newton's third law? Okay, last one on page 5. Now, if we went to an ice skating rink, we could try this. But today, now I did forget my rollerblades, okay? I did forget my rollerblades. But imagine I had rollerblades on, okay? My cart here has wheels on it. I don't have wheels today. Anyone got a skateboard? That would work? No? Okay, forgot my skateboard too. But what happens on this one, person A, person B, they're on smooth ice. And so we neglect what? Friction, so no friction. Can I take away the friction with my shoes and the ground today? No, so we can't do that. Watch my upper body. Because if I was on ice, wouldn't my lower body go with my upper body? I hope so, okay? And so I'm gonna just push on my rolly cart and I'm gonna give it a good push so we see more effect. So watch my upper body. 3, 2, 1. Now, what did my upper body do? It went back. Why did my upper body go back? Why did I go back? Right. I push on the cart pushes on me. Now here, it's person A, person B. Rank the net force on A and B. So who experiences a greater net force? Well, maybe we need to consider overall forces. So person A has what force is acting on it? Gravity, right? We always have a weight. And so the gravitational force, there's a surface. So there's also a normal force. Go in what direction? Up. How big do I draw it? Because we saw last time with our force diagrams, it's not always equal to gravitational force. Is it here? Yeah. Is it on a ramp? No. Are they pushing each other at angles? No. And so it's going to be equal and opposite. Newton's first law, right? So those are Newton's first law. Those balance. But then person B is going to push A to the left, right? And so this is the force on A by B. And no friction, that's it. And so if the two verticals balance, then the net force on A is equal to the force on A by B. It's an applied force. You could also call it an applied force. What about the force diagram for person B? Maybe I draw it underneath. And so this is for B, up there is for A. What would B's force diagram look like? Has weight as well. And if we look at the mass, it has a bigger weight. So maybe we can draw a bigger FG. It's on a surface, not moving vertically. So Fn would be same as gravitation. So, I might blend over, but this is the normal force on B. Those are equal and opposite. I'm just giving 2 tick marks because I want to make sure it's different than the others. It's frictionless, so the only other force acting on B is A pushing on B. What direction is that going to go? To the right. So this is the force on B by A. Again, it's an applied force. And if the first two balance, our verticals balance, then the net force on B is just going to be that applied force, right? So the question is, compare these two forces. If they both equal a net force, well, notice I got nitty-gritty. I got the reversibility. Hint, hint, these two forces are equal and opposite in direction, y'all. That is Newton's third law, okay? These are an action-reaction pair, okay? Newton's third law, Newton's third law. They are one time on each object, and I have 2 separate objects. And so our answer to the first ranking is equal. So these two forces are equal. Or you can say force A is equal to force B. The reason, Newton's third law. I push on you, you push on me. Now, acceleration. Are they going to have the same acceleration? No, specifically net force, whether you say sigma F or Fnet, either one is fine. You're summing the forces that don't balance out, right? Well, we only have those pushes. Well, Fnet equals ma, mass times acceleration. If they have equal or same Fnet, who gets a greater acceleration? The smaller mass. Remember, Newton's second law is about the relationships of the variables. And so that's an indirect relationship. So who's going to have a greater acceleration, person A or person B? A. So the acceleration of A is going to be greater than the acceleration of B. And it's because of the inverse relationship with the mass, because they have equal net force. Okay, how do we feel? Concepts, we ready for some numbers? Yes. It would just continue at a constant velocity. Unless you give it an unbalanced force, it's going to keep doing what it's doing. Inertia. Yes? Constant speed, it'll keep moving in a straight line. Now, we don't see that on Earth because if I throw a ball, right, gravity wins, it becomes a projectile, right? And so it will accelerate. You'd have to go to like outer space, or the hockey puck on ice is our best other example. So overall, in a short window of time, that hockey puck on ice is going to travel at a constant speed. Over a long distance, friction adds up, right? It'll eventually come to stop, but it's not going to, this room, it would be much greater than this room. I showed y'all the video, yes? Hockey puck on ice. That was a long frozen creek bed, river bed, right? It was pretty long. And we didn't even see it come to stop. I think it hit a bank. And so theoretically, if you get your hit right, it would just keep going, right? Did that answer the question? Kind of, sort of? You want to give me a follow-up? If it was what at a constant velocity? Oh, so the collision, you said the word collide. Collisions, hold tight, wait for January when we study momentum. So it's going to transfer some of that momentum to the second object. Now, forces are still involved, but we're just not going to momentum yet. But yeah, there's a direct correlation between forces, Newton's second law, and momentum. Okay, just hang tight, one step at a time. Forces right now. Okay, let's make sure someone at your table has a calculator. Now, just for time purposes, I'm going to go on and skip this page. It's one of those tipper pages. It hits on concepts. So I'm going to have you try this one later. Okay, today I'll be working on, editing our key. And so hopefully I'm able to post the key if you want to check yourself. But notice you've got two blocks. I push on A. Do I push on B? No, A pushes on B. So just be ready, kind of like our stack of books. Look at, maybe the individual boxes, but also you can view it as a collective, right? A system. So try this one later. If we have time next class, I'll come back to it. But we need to start calculating. And so pages 7 and 8 have our calculations. We're going to start basic and work our way up, all right? And so hopefully the first two feel easier, okay? Question 1. Estimate the net force needed to accelerate. Well, I've got a 1,000 kilogram car at 1/2 g. Wait a second, is that grams? No. If you accelerate at 1/2 g, I don't think we've talked about g's plural yet. Anyone training to be an astronaut? I mean, today is like space day or something, right? Our theme for the week. We got an astronaut in the back. David, you're an astronaut. You have the helmet for it. I know, it's like Mandalorian, right? Okay, I was just joking with you. But astronauts, if you train to be an astronaut, they're going to test how many G's you can withstand, okay? G-force, G's. Have you heard this phrase? Anyone ridden Titan at Six Flags? According to their website, you'll experience a maximum of 4.5 G's. Anyone black out like I did? Yeah, okay. That's just the blood leaving your optic nerve. It's okay, it comes back. I didn't pass out. I knew what was going on. I was awake. I just couldn't see. It was kind of scary the first time, but then I knew what to expect. So what is this G's? It's an acceleration, okay? It's factor of 9.8. And I didn't want to use our rounded 10. I don't want you to think it's random 10. So it's how many factors of G's? How many factors of 9.8? So it's just another way of stating the acceleration. And so on Titan, 4.5 G's, at some point you're accelerating 45 meters per second squared. Okay, that's 4.5 more than an object in free fall. Okay. And so 1,000 kilograms, what is that? What did they just give us? Mass. Now I want to give you a heads up. The second example says a 200 G apple. What is that? Is that an acceleration? It's still mass, but it's grams. okay? And so watch out. If you accelerate at 1/2 g's, it's an acceleration. But if they say it's a 200 g apple, they're giving you the mass in grams. Now, which one's SI, kilogram or gram? Kilogram. So kilogram is good, but we need to convert grams to kilograms so that we end up with a Newton, okay? Remember, a Newton is equivalent to a kilogram times meter per second squared. And so maybe you did a little dimensional analysis last year. You can use the conversion factor, or I'm doing the little T chart. Or maybe you just know how to convert, but you got to convert, okay? And so 1 kilogram has how many grams? And if you don't remember, flip your formula chart over. They do give you SI prefix common in this class. So what does kilo represent? 1,000 or 10 to the third, either way. And so to find out how many kilograms, 200 divided by 1,000, you move the decimal 3 places to the left and get 0.2 kilogram. Good deal? And so this first one is just introducing G's as an alternative way of giving acceleration, but also addressing the gram kilogram. And so estimate the net force. We're going to do both of these together. Net force, they give us mass. We know the acceleration. And so net force equals mass times acceleration. Now, we don't know if these apples and cars are moving or not, so I'm not going to really draw a diagram. It's just, what's the net force? MA, Newton's second law. And so we take our 1,000 kilogram car times half of 9.8, and I'm going to go in and show the steps. Now, with our math, if you want to go on and use 4.9, go for it. Let's just do 10, right? Half of 10 is 5. 5 times 1,000 is 5,000. Now you can say kilogram times meter per second squared, or it's equivalent to a Newton. Same thing with our little bitty apple. And so Fnet equals the mass of the apple, 0.2 kilogram, at the same rate. And so 1/2 of 9.8 or 10. And so that's going to be 10, half of 10 is 5 times 0.2 is what? 1/5 of 5 is 1 Newton. There you go. Good deal? Okay. Question 2 is still about average net force, average because it's not always constant when you drive a car. But look at what also they give you. What is the average net force required to bring a 1,500 kilogram? What did they just give me? Mass, okay? I was waiting for somebody to say weight. FYI, sometimes the problems will give you mass, sometimes they'll give you weight. Is it the same thing? No. Weight has mass times our 9.8 acceleration due to gravity. And so just be aware, tomorrow it might say, 1,500 newtons. That's the weight. But 1,500 kilograms is the mass of the car. And it says it's going to come to rest from a speed of 100 kilometers per hour, yuck, yuck, right? Not SI unit, another conversion, within a distance of 55 meters. Well, goodness gracious, they're giving me velocity, and a distance. Do we have that in our forces? Force equals Fnet equals MA. Why would they give us kinematic stuff again? What's the connection between kinematics and forces? What do they have in common? Acceleration. So yeah, you may still be doing kinematics, to find acceleration so that you can do forces? Or what if they give you force information and then you use kinematics to find time of an object, right? And so kinematics isn't going away, but maybe instead of a 3-part kinematic problem, it's 2-part force, 1-part kinematics, right? And so first, before I can find the net force, I need that acceleration. But actually before that, before kinematics, we got to convert kilometers per hour, although it's common in some places, it's not SI. And so we want to convert that 100 kilometers per hour. So you can use that T chart again, or the other way is to use ratios, right? And so it doesn't matter which one you convert first. I'm going to go for the kilometer. And so we want kilometers to meters. 1 kilometer is how many meters? 1,000 or 10 to the third, either way. And so kilometers will go away. Now, if we stop, it would be meters per hour. We want meters per second. So 1 more conversion factor. Get rid of hour. Now, maybe you don't know how many seconds are in 1 hour. You could go to minutes, but let's talk it out. 1 hour has how many minutes? 60. And 1 minute has how many seconds? 60. And so 60 times 60 is, careful, 3,600. Careful, you got to make sure it's not 360. 60 times 60. And so notice 100 times 1,000 over, 100, not 10, over 3,600. So work it out. You can even reduce before you keep it going. And so plug it in. What do we get for this velocity in SI units? 27.8 sounds familiar. And the units that didn't cancel are meters per second. That's it, meters per second, right? By the way, AP typically doesn't give you kilometers per hour. Now, I have seen problems where you have to do the hour to second conversion or separately kilometer to meter. But in terms of speeds and velocity, most times they give you meters per second. This is an old textbook question. Kilometers per hour is a more realistic speed, okay? Miles per hour, I don't think we would even do. All right, so what was this? It said from this speed. So this is our initial velocity, and we're going to a final velocity to rest. And they told us the distance or displacement was 55 meters. We said we're going to use kinematics to solve for acceleration. So look at our formula chart, or maybe you have them by heart now. So which equation are we going to use to find acceleration? 1, 2, or 3? Remember, notice we don't know time. So which equation doesn't need time? 3. We're going to use the third one. And so VF squared equals VI squared plus 2A delta X. So we're coming to a rest. So 0 equals that 27.8 squared plus 2 times A times 55. And so you'll need to square the 27 number and then subtract it and then divide by the product of 2 times 55. Notice we'll get a negative answer, and that's okay. If you're going forward, slowing down, that's a negative acceleration. So plug and chug it. Let me know what you get. 7 point what? 03. I mean, yeah, you can keep that. Honestly, 7 is probably good enough either way. And so there's our acceleration. Everybody good? Old stuff? Okay. Now that we know the acceleration, can we get back to the forces? They wanted the net force. And so we know the mass, 1,500. Acceleration is that -7. And again, kilogram times meter per second squared. So work it out. Let me know what you get. Say again. Okay. Yeah, it would be negative. And that just means it's in whatever direction you're accelerating, right? Mass can't be negative, but acceleration can. And so let me write that a little cleaner. Net force equals a negative 10,545. And then the SI unit, kilogram times meter per second squared, or simplified, it's a Newton. Everybody good? Yes. Yeah, you could have called it 7. I mean, honestly, I probably would have called it 7, but you know, it's not a final answer. So I've taught y'all don't round too much till the end, right? Even that 10,545, it's technically too many sig figs. If this was an answer in the back of the book, it would probably be 10,500, just FYI, okay? Usually 2 or 3 digits is the rule of thumb for sig figs of final answers. Okay, so number 1 and 2, those are basic intermediate plug and chug. Now what we're about to do is actually more of what you're going to see more on a daily basis, okay? They give you a scenario, you got to draw a diagram, because they're not just asking for net force. They're asking for a specific force, okay? So whether they ask for friction or tension or normal, y'all, we don't have equations on the formula chart for those. You got to go through an Fnet statement. You got to go through, you got to draw first a diagram. And so number 3, before I start writing stuff, let's do a little talk about elevators. Now we could field trip to the other end of the building, all get on the elevator, but it's only a 2-story building. Are we really going to notice anything? No. And so if you know of a 10-story building or whatever, maybe your parents work in a building that has a really good elevator over many, many floors, right? Go get in, or think back to the last time you rode an elevator. When the elevator goes ground floor, doesn't have to go to the top, but it just goes up. It goes from rest, it accelerates up. How do your legs feel? This is not a common question, right? We just ride elevators. We don't know how our legs feel. But do you feel like, oh, I'm getting pushed into the floor? My legs feel heavy. Or take it to the extreme. I mentioned Six Flags earlier, right? Titan. Have you ever rode Superman Tower of Power? I never have, but I've watched it. It's just an elevator. It goes up, it comes down. You sit down on a seat, you go up, you come down. Now, why I don't ride it, these are not calm transitions. They launch you up. It's a high acceleration, and my stomach just can't handle that, okay? But it's an elevator. You go up, you go down. So for somebody who's ridden Superman Tower of Power, raise your hand so I know who. Okay, so we got a couple. How do you feel when you go up? It's like you're being pushed down, right? Your body wants to stay down, but the pressure you feel with the seat is just responding to the seat pushing on you. What direction? You're being pushed up, right? You feel heavy. Now, fast forward, you're at the top, they hold you there, and then they drop you. Ooh, I came out of my seat a little bit. I feel light. I feel like I'm in free fall, right? I really, truly don't know if you come off your seat, but there's less pressure with the seat. The seat pushes on you less. You feel lighter on the way down, yes? Okay. Now this problem is a person riding an elevator. It's going to accelerate 0.4 g. That's not grams. That's an alternative way of giving acceleration. But look at the first question. What does the scale read in newtons? And you're like, what scale? So maybe I should tell you that physics types are a little quirky. Imagine you rode Superman Tower of Power while sitting on a bathroom scale. I went out and bought a scale just for this. We used to have one, couldn't find it. But think of a bathroom scale as just a force sensor, right? That's all it is. It's giving a force reading. Pounds, newtons, who cares? It's a force. And so how do we normally get our weight? You know, you go to the doctor or whatever, you stand on the scale. Do we sit there and jump up and down? No, the doctor will tell you to stand still. And so you get an accurate reading when you're at rest. Then the normal force provided by the scale is equal and opposite to your actual weight. Yes? So at rest is how you get an accurate weight. But if you were to jump up and down, what's the scale going to do? It's going to go up and down. It's going to fluctuate, right? High number, low number, high number, low number. And the truth is your weight's somewhere in between, right? But what if you were to get on Superman Tower of Power or go to that really good elevator and stand on a bathroom scale? I know you're like, what? I know, physics types, weird stuff. But that's what we're doing here. Moral of the story, bathroom scale is going to respond to what the floor is pushing on you. It's a normal force reading, okay? So when it says, how much does the floor push on them, we're going to end up solving for normal force. That's it. Don't look on the formula chart for the force of a bathroom scale. It's just responding to the situation. And moral of the story, when you ride an elevator or Superman Tower of Power, or even the hill roller coasters, don't you feel the pressure and lightness when you go up a hill, down a hill? You still feel that, okay? It's just not straight up and down. Normal force is not constant, okay? We saw it with ramps, we saw it with shopping cart, and we're seeing it here with the elevator. Everybody good? Okay. So it all begins with a force diagram. Now we have 3 different scenarios, so I'm going to draw 3 different diagrams. Similarities, but differences. And we're solving for the scale reading on all of them, okay? And so for A, it says, what does the scale read in newtons? Well, back up in the prompt, we've got the mass, 70 kilograms, that's good. And they're accelerating upwards. Now, for all 3 scenarios, we have to assign a direction, positive direction, negative direction, and just be consistent. And so what do y'all want to do? What's positive, up or down? Up, okay. So we'll say up is the positive direction. And that's going to be true for all scenarios. We accelerate upwards at 0.4 g. Again, that's not 0.4 grams, that's 0.4 times 9.8. Now for our verbal math, let's just call it 10. And so 0.4 times 10 is 4. So that's our acceleration, 4 meters per second upwards. Okay, so diagram. We've got weight down. And as you accelerate upwards, if acceleration is upwards, that's the positive direction. Won't we also have a net force in the positive? Remember Newton's second law, Fnet equals ma. Mass doesn't have a sign. And so if you have a positive acceleration, you better have a positive unbalanced resultant force. How big do I draw normal force? Equal, less, or more? You're accelerating upwards. You feel heavier. You feel squished into your seat, right? The pressure. You weigh, theoretically, more, right? At least that's what the scale tells you. And so it's going to be bigger. So that when we step 2, sum the forces, I'm going to go with a positive normal plus a negative or minus Fg. Okay? And so if I want a leftover positive net force, my upward force better be bigger, okay? And so now we got to move things around. They want us to solve for Fn. Before we do numbers, let's solve it. And so I got to add Fg to the other side. And so Fn would equal the Fnet plus Fg. Now we don't know the numbers yet. Let's do some equations. Newton's second law says Fnet equals what? Ma plus Fg is your weight. We said it earlier, weight equals mass times gravity acceleration. Okay, so it is a mass times acceleration in both pieces, but the ma is the acceleration that you're actually going, and g is based on the gravitational field, which unless you leave the Earth, it's not going to change. Okay, now yes, you could factor out mass, but I'm going to keep it because later on I'll be asking you the weight. So it's nice to solve for it at some point. And so mass 70. Our acceleration is 4. And then mass is 70. And we're going to go with 10 instead of 9.8. Okay, just so we can make nice numbers. Now, some of you are thinking, Ms. Earhart, isn't G negative 9.8? Actually, no. G is a positive value. G, the gravitational field of the Earth, is always pulling us to the center, right? Plus, we've already said Fg was a negative force. You don't want a double negative, okay? And so it's a little different. With 2D kinematics, we said G, acceleration, negative 9.8. But didn't sometimes we use maybe positive if the object only went down? So even then it was subjective. You had to look at, direction, how you define it. So I've already defined down as negative. I've already said the sign of the original force of gravity was negative. Don't double negative, okay? Okay. And so 700 plus 280 is 980, and that's newtons, equals the normal force when you're accelerating upwards. Isn't that more than our weight? Our weight is 700, but the scale is reading 980. Oh no, I ate too much pizza last night. No, it's because you're accelerating. The scale's responding to the situation. Good deal? Okay, next two should go quicker. We're going to do the same thing, except now on part B, when the elevator is going down, what does the scale read? And so what's not said here, we're going to assume it's the same acceleration, just in the downward direction. So it'd be that negative acceleration, and we'll go with that -4. Okay. Well, our diagram is going to look a little different. What would our diagram look like now when you're going down? Well, we still have up as positive. We still have the same actual weight. But on the way down, now we feel lighter. Why? Because the floor, the seat, is pushing on us how much? Less. Normal force is smaller when you accelerate downwards here, okay? And plus, if you're accelerating downwards, negative acceleration, don't you want a negative net force? So the negative force, whatever it is, needs to be bigger. So you have unbalanced left over. Same Fnet statement. Again, up is still our positive direction. So I'm going to go Fn minus Fg. We still got to add the Fg to the other side. And so Fnet plus Fg is still Ma plus Mg. But now, what am I going to plug in for the acceleration? Not a +4, but I'm going to plug in a -4. Weight technically stays the same. And so now instead of adding 280, we're going to subtract 280. Normal force on the way down, the bathroom scale would read what? Say it louder. 420, okay? Newtons, okay? So on the way up, 980. On the way down, 420. If I was standing on the ground on the scale, it would read what? Actual weight, 700 in between, right? C, what if we're still in the elevator, but now we're going a constant speed. And notice they don't say if you're going up or down. Doesn't matter. It can be true up or down. What's true if you're moving at a constant speed? Acceleration equals 0. Newton's second law says Fnet will equal 0. Y'all, this is Newton's first law when you have balanced forces. What would your diagram look like now? We've got gravity, same weight as before. Are we going to have a bigger, smaller, or same normal force? Same. Equal and opposite. Newton's first law. And so now you could just say, hey, I already know these two are equal and opposite, right? Or you can go through your Fnet statement. And so watch this just as an option. We said Fn minus Fg, up minus down. Solve it for Fn. This is all the same as before. But now Fnet equals 0 plus your 700. So normal force would equal 700. It's the same as if I was just standing on the ground, standing on the scale. Okay? Again, these are the two states of equilibrium, at rest or constant velocity. Everybody good? You'll never ride an elevator the same now, right? Now you're going to take a bathroom scale on the elevator. No, I honestly never have. There's YouTube videos for it. But when I do ride rides, I do notice, oh, this is my legs feeling heavy. Oh, this is me feeling lighter. Oh, there's more normal force. Oh, there's less normal. So I think about it. I just haven't ever taken a bathroom scale. They give you looks, right? All right, new problem. Number 4 at the bottom, okay? And so again, we're gonna do this one and then hopefully get one more started before we end. Number 4 at the bottom, no more elevator. Let's go back to the ground. We've got a box that has a mass, they literally said mass, 50 kilograms. So if they didn't say mass, hopefully the unit gives it away, right? This is mass, it's not the weight. It's pulled with an applied force of 400 newtons. If the box starts from rest and is pulled 192 meters in 8 seconds, what did you just hear with those 3? What's running through your head? What K word? Hello, hello, is this thing on? Meters per second, meters second, kinematics, right? And so we're going to have to do kinematics at some point. What is the force of friction? So we'll also have to do forces, okay? And so maybe you don't realize kinematics yet. So I'm just going to pretend, we didn't do that. They do tell us, assume FA is constant. Now, if you were to push or pull a box, are we robots? Can we push and pull constant force? No. And so in my mind, I think, well, what if I had some kind of robot that could pull or push this object? And so force diagram, we've got a floor. Here's our box. Here's what we'll call the center of mass. What forces are acting on this object? Gravity, gravitational force down. What else? Normal force goes what direction? Up. How big do I draw it? It'll be the same. Are we on an elevator? Are we on an incline? Is this a shopping cart? Did they give me an angle? No, no, no. And so this is back to that equal and opposite balance of normal force and gravitational force. What else? They tell us we're applying a force. Do they specify what direction? No, so we get to choose. How about standard sign convention? Y'all want up and to the right to be our positive direction? Yeah, it doesn't have to be, but my rule of thumb, don't change, don't leave the standard unless there's a reason. Here, there's not a reason to. So I'm gonna say, let's pull to the right. They talk about friction, so I better have it on my diagram. What direction will friction act? To the left, right? Parallel to the surface. How big do I draw this force of friction vector? Equal to FA, more than FA, less than FA? Well, let's think. We have kinematics, right? Probably not going to be constant velocity, right? They'd have to give you some kind of steadily or constantly, uniformly, right? And so we'll assume it's going to accelerate. And if we were to do it, we will in here in a second, the acceleration should come out positive. You start at rest. So it's going to speed up in the forward direction. And so if I'm going to have a positive acceleration, I want a positive net force, which means I better have a bigger positive force, a bigger applied force. How big do I draw friction? Smaller. Okay, so friction is less than FA. Good there? All right, I'm going to keep going with forces. Maybe you don't realize you need to do kinematics yet. And so next step is that force statement, net force statement. Now notice I've got X direction, Y direction. Hopefully you've learned by now, since projectiles, X and Y are independent of each other. I can't put them all in the same statement. And so I'm going to have Fnet X and Fnet Y. Okay. So Fnet X, sum the forces in the horizontal. Now we said to the right was positive. I personally like to start with positive. You don't have to, I like to. And so I'm going to say FA, friction acts the opposite direction. So I'm going to say minus friction. Fnet Y, sum the forces in the Y. Up, I said, was positive, so I'll say Fn minus the force of gravity. Those are Fnet statements. These are the equations we use to solve for normal force, solve for frictional force. If I sent you on a scavenger hunt of the formula chart, I promise you won't find a single Fnet statement. The only thing close is Fnet equals ma, which we'll do here. Both of these have ma, but notice I'm using ax and ay. The acceleration that this box is going to have will be in what direction? Y'all know this. It's a box moving in the horizontal. It's going to accelerate in the horizontal. What's your acceleration in the vertical? 0. This is going to zero out, which means Fg and Fn are equal and opposite. So we've got Newton's first law in the vertical, but not so much in the horizontal, okay? And so they do give you Fa, and we are going to be asked to solve for friction. And so if I was to add friction to the other side and then subtract ma from both sides, careful here, I'm doing 2 steps in one. Friction force equals the applied force minus max. They give you applied. They said it was 400 newtons minus mass. They gave me the mass, 50 kilograms. However, they did not give me the acceleration. At this point, you would be like, oh, I gotta go use kinematics to find the acceleration, okay? So pause on forces. Let's go do some kinematics. And so they said it starts from rest. Don't we love kinematics by now? Oh, not yet? I asked that question too soon? Okay, I'll ask again in December. Okay, so it starts from rest, VI equals 0. It's going to travel a distance or displacement forward, 192 meters. No change in direction, distance, displacement, same thing. And they give us the time, 8 seconds. Now we're doing all this to find the acceleration. You'll notice acceleration is what links kinematics to forces. That's the in-between, okay? And so looking at your equations or knowing your equations, which one are we going to use to solve for acceleration? Not the first. I don't know the final velocity. I could find it, or I use the second. And so we'll use this second equation, delta x equals VIT plus 1/2 AT squared. VIT, thankfully, don't we love it when we start from rest? And so we get 192 equals 1/2 A, and then time, don't forget to square it. So 8 squared is 64, half that is 32. And so what's 192 divided by 32? I think it comes out real nice. 6. And so now that we have the acceleration, we can go plug it into that force statement. And so 50 times 6 is 300, and 400 minus 300 is, that's a lot of silence for 400 minus 300, 100. You're like, it's so easy, she doesn't need us. I like participation. So we get 100 newtons for your frictional force. Now, that's a magnitude. That's a magnitude, FYI, because we already did the direction. If we had said every force was positive, we would have solved and got a negative friction. We already said it was negative, right? Up in our original statement, right? And so if they ask magnitude and direction, you don't have to do anything different. You just say, oh yeah, I said it was negative, negative, backwards, whatever. Good deal? Okay, we're just gonna get the next page started, okay? Bear with me a couple more minutes. Page 8. We're still gonna apply a force to a box, but this time we're gonna use a string. Typically, when you apply a force with a string, what do we transition to? What do we call that force in a string? Tension, okay? As long as you don't start saying, oh, there's an applied force and tension. No, pick one. Typically, I go with tension. And also notice, we're not just pulling or pushing it parallel to the floor. We got a what? An angle. Are angles important in physics? Yes, make sure your calculator's in what mode when dealing with angles? Degrees. And so forces, you still want to be in degree mode. Okay, here's our prompt. A man pulls a 50-kilogram box. What did they just give us? Mass. Oops. Do I need to convert it? No, kilograms is good. And they pull it at a constant speed. What's running through your head? Constant speed means zero acceleration. What does that mean for forces? Does that mean there's zero forces acting on the object? No, it means net force equals 0. In other words, this is a Newton's First law. So we pull it across the floor. He applies a 200 Newton force at an angle, and that's supposed to be 30 degrees, just like you see in the picture. Okay. Sum the forces in the X direction, and then that means write an Fnet statement, and then find the frictional force. Sum the forces in the Y direction, and then what's the value of normal force, okay? And so it all starts though with what they didn't tell me to do. Let's draw a diagram. What forces are acting, not on the man. Is the man the object? Here's how you know. What did they give you the mass of? The box. They did not give that to me for the person. Yes. And so it's the box. That's our object. And so we've got weight. And we're pulling with a string. So I'm going to call it a tension force. And that tension force is at an angle. By the way, on the AP exam, you are not allowed, they do not give credit if you draw components. It used to be that the components had to be dashed lines, but you know, teenagers, they don't always follow the rules. They solid line it. No, you don't have 3 tension forces. And so now they say not drawing components. Here's what I would suggest. Draw your chicken scratch one with components on the side. And then on the official diagram where they give you a dot, draw it without components, okay? So official and your chicken scratch, okay? So I'm drawing a chicken scratch. It's a working force diagram. What other forces are acting on this box? 2 more. Friction is going to act what direction? Remember, the rule is it's parallel to the surface. So it's not, we're pulling northwest, but what direction will it actually go? Just west. And so parallel would be to the right. Now, how big, I should have asked, how big do you draw it? It shouldn't equal the tension force, but it should balance out the other horizontal force. So maybe a little bit bigger. Just extend that arrowhead. It should be equal and opposite the X component. Why? Because we're pulling it at a constant speed. One other force, which is it? Normal force. It goes what direction? Up, perpendicular to the surface. How big do I draw it? Smaller. We're lifting up a little. We're pulling up. Is the box levitating? No. But is there less pressure with the floor? Yeah. And so it's going to be smaller than your gravitational force because together the 2 ups are going to balance the downs. All right. Okay. We will actually do the A and B next time, but it all starts with a diagram. Okay. All right, we only have 1 more class, and so I believe I'm going to have to pass over the tipper questions on pages 9, 10, and 11. And so next time, my goal is page 8, 12, and 13. So if you want to try some of the tippers ahead of time, you can. Again, I'm going to post the key in Canvas for those that want to check later today.